Okay, hello everyone. Today we will talk about line graphs and edge coloring. Our outline is line graphs, edge coloring, chromatic index, multiplicity, Koenig's theorem, one factorization, Wissing and Gupta's theorem, graph class, Shannon's theorem, characterization of line graphs, Krauss theorem, Van Rooij and Fifth theorem, Beinecke's theorem, and examples. Okay, what is line graphs? A line graph of G. This is, for example, this is a graph, and this is its corresponding line graph. The edges are mapped to vertices, and the vertices are connected if the edges are incident with the same vertex in G. Line graph properties are: line graph of a cycle is a cycle. Line graph of a clique may not be a clique. This is a counterexample. Line graph of a planar graph may not be a planar graph. In fact, we found a long proof, but we didn't put it here. Line graph of a tree may not be a tree. This is a counterexample. And maximum independent set in a line graph corresponds to maximum matching in the original graph. This is original graph. This is maximum matching, and this is maximum independent set. They are dual problems. Beinecke showed that there are 9 minimal graphs that are not line graphs, such that any graph that is not a line graph has one of these 9 graphs as an induced subgraph. That is, a graph is a line graph if and only if no subset of its vertices induces one of these 9 graphs. 1, 2, 3, 4, 5, 6, 7, 8, 9. For example, a line graph cannot have a claw, as a subgraph because in real graph G it corresponds to an edge with 3 endpoints, which is impossible. Here, this corresponds in real graph an edge, and these are endpoints, but an edge cannot have 3 endpoints. Okay, an edge coloring of a graph is an assignment of colors to the edges of the graph so that no two incident edges have the same color. As an example, we have here Desargues graph, a 3-edge coloring. Here, for example, for this vertex, one of the incident edges yellow, green, blue, and red. In fact, edge coloring is a subproblem of graph coloring, which is a subproblem of graph labeling. And edge coloring and vertex coloring and face coloring are in the same family of problems. Edge coloring. Edge coloring problems arise when the objects being scheduled are pairs of underlying elements. An example of edge coloring is, for example, edge coloring of K2n, complete graph with K2n vertices. In a league with 2n teams, we want to schedule games so that each team plays exactly 1 match per week. Since each team must play with 2n minus 1 matches, the season will last 2 and minus 1 weeks. The games of each week form the matching. We can schedule the season 2 and minus 1 weeks if and only if we can partition edges of K2n into K2n minus 1 matrix. Since K2n is K2n minus 1 regular, all weeks matchings must be perfect matching. Figure on the right gives the solution. Put one vertex in the center. Arrange the 2n minus 1 vertices cyclically. This is viewed as congruence classes modulo 2n minus 1. Okay. Edge coloring problems ask whether it is possible to color the edges of a given graph using at most k different colors for a given value of k, or with the fewest possible colors. For example, here, fewest possible colors is 3. This is the graph G, and this is its corresponding line graph LOG. As you can see, for this edge, we can have vertex here. So the edge coloring problem becomes vertex coloring problems here. Okay, then we have chromatic index. But before, we want to know chromatic number chi of G. The chromatic number of a graph G is the smallest number of colors needed to color the vertices of G so that no two adjacent vertices share the same color. And for the edges, this was for vertices, and for the edges we have edge chromatic number chi prime G, also known as chromatic index. The minimum required number of colors for the edges of a given graph that no two edges incident to the same vertex share the same color is called chromatic index of the graph. And as a result, normally chi prime of G is bigger than delta of G. Delta of G is the maximum number of maximum of the degrees of the vertices. Here, for example, vertex 2 has degree 3, and vertex 4 has degree 3, and others have 2. So maximum is the degree 3, and it is normal to expect that chromatic index should be bigger than this, should be bigger or equal, because at least we will color these edges. So it should be bigger or equal. Then Weising and Gupta proved that delta of G plus 1 colors are sufficient for simple graph chromatic index. We will see it later. Also, we will see the proof later. Here we can say that chi prime of G, chromatic index of G, is equal in fact to chi of L of G, which is chromatic number of L of G. It is K, which is 3. So then we have multiplicity. Multiplicity in a graph G with multiple edges. We say that a vertex pair xy is an edge of multiplicity M if there are M edges with n points x and y. We show by Greek letter mu mu xy is equal to m multiplicity of the pair x and y. And mu of g is the maximum of these multiplicities. For example, here mu of g is 4 because all vertices have multiplicity 4. For loopless graphs with multiple edges, in fact multiple edges means this is not a simple graph, chi prime of g may exceed delta g plus 1. Shannon proved that chi prime of g is equal to 3 delta g over 2. We will see also Shannon theorem later. Weising and Gupta proved that chi prime of g is equal to delta g plus mu of g. In fact, we will see the proof of the formula for the simple graphs, which is chi prime of g delta g plus 1, and for non-simple graphs we won't see the proof. The proof is not put here. Okay. Firstly, we will see the Kering's theorem. If g is bipartite, then chi prime of g will be equal to delta g. So, what we will do? Prove for k bigger than 0, every k regular bipartite graph has a perfect matching. The proof of this is, let G be a k regular xy graph. So for every x, for the x part and for the y part, they should be equal, and as it is k regular, we have kx times kx equals ky. Consider s in x and corresponding ns in y. Let m number of edges from s to ns, and size of the ns is equal to m. Since g is k regular, we know that m is k times s, and we know that m is smaller or equal to k times ns. So s is smaller or equal to ns, and this corresponds to Hall's condition. So this proves this corollary was in the Book of West 3.1.13. By induction on delta of h, this yields a proper delta h coloring. So if we show that for every bipartite graph G with maximum degree k, there is a k regular bipartite graph H containing G,